Okay. So hello everyone. So welcome to attend our this week's Rutgers Efficient AI Seminar talk. And today we're glad we have the Professor Huang in Tsinghua University to give us this talk, Dynamic Neural Network for Efficient Inference. Professor Huang is assistant professor in the Department of the Automation at Tsinghua University. He received the PhD degree from the Tsinghua University in 2015 and was a postdoc with the Department of Computer Science at Cornell. His research interests lie in machine learning and computer vision. He authored about 50 papers on top-tier conference and journals, including ICML, NURBS, ICLR, CVPR, ICCV, CCV, TPMI, and so on, and have collected more than 20,000 citations. His work on DenseNet, I think many of you know that, won the Best Paper Award of the CVPR 2017. So now let's welcome Professor Huang to give us this talk.
Okay. Thank you, Professor Yang, for the introduction, and thank you for the invitation. It's my great pleasure to share some of the recent research of our group. So the topic today is on dynamic neural networks for efficient inference. Is the outline for the talk. First, I will have a recap of the deep CNN architecture design in the past decade. And then I will talk about 3 types of dynamic neural networks, the sample-wise dynamic networks, and the spatial-wise and the temporal-wise dynamic networks. Okay. So convolutional networks has been very successful in the past decade, especially in the field of computer vision. And we have witnessed many popular architectures. For example, the AlexNet, which is a milestone in computer vision, and of course in the whole deep learning field. And the VGG network, the Inception or GoogleNet, and the ResNet, DenseNet, and the high resolution network or HRNet. So these are the some of the typical convolution networks developed in the past decade, and of course these architectures are pushing forward the research on deep learning, and this slide basically summarizes why the architecture design in deep learning matters. So basically, there are 4 key factors. First, the architectures affect the representation power. Different architectures may have different representation power, and many of the successful networks have very high representation power, such that they can fit complex functions and to handle very complex tasks. And then the optimization property. The different architectures have very different optimization characteristics. For example, the ResNet, why ResNet can be extended to hundreds of layers is because with those skip connections, we can easily train a very deep architecture. And without these skip connections, people struggle to train a network which exceeds tens of layers. And the generalization property also depends on the architecture and of course the efficiency, right? Which will be our focus today. And I roughly divide the advances of the design of deep convolutional networks in the past decade into 3 stages. And in the first stage, I call it fast developing stage. That is, people will design networks that can achieve higher accuracy on those benchmark data set. And in this stage, the architectures have very high diversity, and some of the architecture may look very fancy, but those architectures can indeed lead to higher accuracy. So some of the representative networks include the IMAXNet, VGG, and the GoogleNet. And in the second stage, I call it the mature stage. And in this stage, people have discovered that the key principles that lead to high performance networks are actually very simple. For example, the ResNet and DenseNet, although they can grow very deep, but the basic component or the underlying principle are very simple. Okay, and so this is from the year 2015 to 2017. And after that, as more industry get involved, some the deep learning has been applied to different applications in our real world. So in this stage, people are designing the networks for different purposes. And a key objective is that people need to design a network with higher efficiency or a better accuracy and speed trade-off. For example, there are many not-weighted models developed for mobile devices. For example, the mobile nets, the shuffle nets, the condensed nets. So these are designed for mobile applications for computer vision tasks. And this is one direction. And another direction is called AutoML, and to be more specific for the architecture design is neural architecture search, or NAS for short. And this is a very popular research direction, and there are many papers developed in the past maybe 4 or 5 years. And dynamic networks, so which will be the focus of this talk, because for most of the networks shown on this slide are static models. And so in this talk, I will introduce why we needed to design dynamic models and how to make the deep networks dynamic. And by the way, there's also a trend recently that is the transformers are getting very popular. And actually, the transformers are a specific type of dynamic models because the parameters are dynamic. I will talk a little bit on this topic, but the focus of this talk will be dynamic neural networks. Okay. So why do we need dynamic networks? We already have the ResNet, DenseNet. So these are very good models that can fit our need in different scenarios. So why do we need to make them dynamic? So here's our motivation. So if we look at this plot, so the vertical axis shows the accuracy, and the horizontal axis shows the computational cost. And here we plot some of the popular convolution networks on this plot. And we can see a clear trend that larger models are doing better than smaller models, right? When we move towards the right, that means if we spend more computational cost, then we will have a higher performing model. Okay, and so we're wondering why we need those larger models, right? Why, when we have a model that have tens of layers deep, we can get a higher accuracy. So we're wondering what is the reason behind this trend. So here is a very intuitive example. So if you have never looked at the image shown here before, probably you may take a while to recognize what's the object in this image. So actually, this is a photo of a horse that is taken from a weird angle, right? We cannot see its eyes, and its nose is right in front of the camera. So this is not a typical image for a horse, and so apparently it's not. It may take a while for we humans to correctly recognize, right? And however, for the image shown here, I think most of us can immediately recognize the horse in this image, right? So if we compare these two images, we can see that for our human visual system, we actually allocate different amount of computation on these two images, right? We can immediately recognize the left image, and we may take a while to recognize the object in the right image, which actually means our brain is dynamic, right? Our human visual system is dynamic. We do not allocate the same amount of computation on these two images. And if we get back to convolutional networks, we will see that no matter for the left image or for the right image, we are using the same model. We always inference the image from the first layer to the last layer. There's no distinction between the inference, the architecture to inference these two images, right? And we recognize, notice that this is actually a waste of computation, because I think for the left image, a very shallow network can do the job well. However, for the right image, it may take a very deep network because it may need some complicated feature extractors to form the concept of a horse, right? And so actually this example explains why a deeper model are doing better than a smaller model, because whenever we make a model deeper, it may recognize some additional images that are very non-canonical, just as the image shown on the right? So, however, if we make a model very deep, then it wastes the computation of those easy images. And actually, the data set in our real world have the non-tail property. That is, the canonical images are contribute the majority of the distribution, while the weird images lie in the tail of the distribution. And this makes the computational redundancy more severe, right? Because we have to waste a lot of computation. We have to inference the left image with our very deep model, but actually it does not need a very deep model. So immediate question is, why do we need to use the same expensive model for all the images? And can we use, a small model to recognize those easy images, right? And use the bigger network to recognize the harder samples. So this is our motivation to develop a dynamic model. We need to differentiate the computation that's spent on those easy ones and the harder ones, or actually, the computation should be conditioned on the input. And then I will talk about concrete examples, concrete algorithms to achieve this goal. Perhaps the most popular way to achieve this dynamic inference is first constructing a very deep model, and we have Okay, so our objective is we need to inference a hard image with a deep model, and then a small and inference an easy image with a smaller model, right? So most straightforward way is to perform the circular early exiting. So just as the size shown here, if we have an easy image, just like the house here, we wanted to exit from a shallow layer. For example, we can attach a classifier to an intermediate layer in a very deep model. And if we gain sufficient confidence, we can early exit this image. So such that for this image, it does not need to inference the whole network. So this is the naive idea, but actually this idea does not work quite well. So the reason is the challenge here is for convolutional networks, it has the hierarchical learning process. And in the shallow layers, it learns those fine level features. And in very deep layers, it learns the coarse level features because it has the downsampling layers in between these stages. And when we attach classifiers, we attach the circular early exits to those early layers, we usually get terrible classification performance, just as the toy figure shown here. And the reason probably because in those fine level features, it has some high frequency noise. And for maybe another reason is the receptive field is relatively small in those shallow layers, because the downsampling layers are, are very the key factors that augment the receptive field, because they can enlarge the receptive field exponentially. So before the downsampling layers, the receptive field is relatively small, and if we attach classifier to those features, then usually the classification performance is poor. So this is a challenge, and only the classifiers attached to the coarse level features can get a decent performance. So this is a challenge here. So to summarize, the classifiers only work well on the coarse level features. And really, if we attach the classifier to all the earlier classifier to the coarse level features, then all the computation has been done before getting to a coarse level feature. So to address this challenge, we developed a new architecture, so which is actually a multi-scale architecture to address this challenge. So in this multi-scale architecture, the input is on the top left, and in this architecture, all the intermediate classifiers we will see that are attached to the coarse level features. So this addresses the problem. In this architecture, all the classifiers can get a decent performance because it all uses the coarse level features for classification. To train this network, we just use the normal training process. We just sum up all the losses of the classifiers and train them as a Euro-static model. However, during the inference stage, we first inference the first classifier, and we will compare the confidence with a given threshold. So usually the confidence is obtained by the softmax prediction, so the largest probability of the softmax output. And we will compare it with a given threshold, and if the confidence is lower than the given threshold, we will continue inference the second classifier, and we'll continue this process until we gain sufficient confidence. that is greater than our threshold. And then if this condition is met, and we will skip the rest, the inference of the rest of the network. And then we will see that for different input, we will activate a different number of layers in this multi-scale architecture. So in other words, the network depth is dynamic, conditioned on different input. So that's why we call it a dynamic network. And this slide shows the results on ImageNet and the CFA 100. So these are two popular benchmark dataset in computer vision. And if we look at the left plot, so the vertical axis shows accuracy, and the x-axis shows the computational cost. And the three black curves shown here represent the results of the dynamic network. We call it multiscale dense net, or MSDNet. So the red dots corresponds to statistical models, to dense net, and the blue squares corresponds to ResNet, and also the GoogleNet and the AlexNet. So so the black curves are on the top left, so which means it uses less computation to achieve higher accuracy. And we'll see the black curves shown here are solid curves, which means actually each point on this plot is attainable. However, for the statistical models, the additional line between two models, between these two models, because there's no models between these, because we do not train any additional models between these two models. And why we can obtain a solid curve here is because we can go back to this slide. And when we have a trained MSDNet, and we can tune this threshold online. That is, we do not need to retrain the network, but we can simply tune this threshold. And if we make the threshold higher, that's the network will be more conservative, right? It will use more samples will exit from later class, such that it will use more computation to achieve higher accuracy. And if we make the threshold lower, then the network will be more aggressive. It will use less computation, but of course the accuracy will decrease. So by tuning this threshold, we can obtain a trade-off curve. That is the solid curve shown here. And we have three black curves because we trained three models. Okay, and actually this is a advantage of a dynamic network in practice, because suppose that we have a different network on a cell phone, and if we use a dynamic model, we can tune the threshold to fit our needs. For example, if the battery is low, then we can tune the threshold lower, and it will consume it will use less energy, right? And if we aim for performance, we can tune the threshold higher, and it will use more computation to achieve higher performance. So this can be done online without retraining the model. But for statistical models, we can the computation is fixed. We cannot have such kind of flexibility. All right. So to summarize, with this adaptive computational paradigm, we can basically achieve 2 to 5 times speed up of a static model. And finally, we have a visualization So we take a look at what are the images that exit from the first classifier. So these are the easy images, and what are the images exit from the last classifier. So these are the hard images. And we take 12 images here, and the first row shows the images from the red wine class, and the second row shows the images from the volcano class. And the images on the left corresponds to the images that exit from the first classifier. So these are the easy ones. And apparently we can see that these images are relatively clean, right? So it's the features are relatively easy to easy for the network to model. And the images on the right are relatively more complex. So these are the harder ones. So for example, the last volcano on the bottom right is a volcano, is a toy volcano, and the network apparently needed more computation to form the right concept. All right. So this is our first work on the dynamic depth network, and so recently we have transferred this idea to the dynamic to the vision transformer, because the vision transformer is a recently developed architecture that shows excellent performance on image classification. So this is the vision transformer architecture, or the VIT. This is the architecture was proposed by a quite popular paper, which called image is worth 16 by 16 watts. And so the basic idea is to split each image into many small patches. So in the paper, they split each image into 16 by 16 small patches. Okay, and each patch is treated as a token. So they have a sequence of tokens. For example, in the paper, they will have 16 by 16, that's 256 tokens. And they put this sequence of tokens to a transformer encoder, and then they retrieve the prediction from MLP head. And this architecture tends to work quite well, especially the variants developed after this paper has been made public. And so we can have a so from the dynamic inference perspective, we can immediately realize that not all images are worth 16 by 16 watts, right? For example, for an image of an image of an apple shown here, the features are quite simple. We do not need to split into 16 by 16 patches. Perhaps 2 by 2 patches are sufficient, right? So if we have fewer tokens, then the computation can be greatly saved. We do not need to split all the images into those tiny patches, and we can like for some easy images, we can use fewer tokens to save computation. So based on this intuition, we developed a dynamic vision transformer architecture. So it's basically a cascade of VITs, and in this cascade, it will first receive an image with very few tokens. For example, 2 by 2 tokens or 4 by 4 tokens, and we will directly retrieve the output and to see if the prediction is sufficient enough or not. So if for some easy ones we can gain sufficient confidence, we can directly exit. We can directly retrieve the prediction without inference the rest of the cascade. And for those hard ones, we will inference larger vision transformer that we have more fine-grained token representations. That is, for example, we have 7x7 split of the image, or have a 16x16 split of the image. So the basic idea is quite similar to what I introduced earlier in the MSDNet. And so it's basically retrieve early exit from a bigger model. However, in this architecture, we needed to develop some reuse module to make it work well, because in the previous architecture, in the MSDNet, when one of the exits is not confident enough, we can continue the feature learning process based on the features we have extracted so far, right? Because it's there's only one network, we can continue the inference stage. However, in this cascade, if the prediction is not confident enough, we needed to start again with a new architecture. And if we do not have this reuse module, then the computation are wasted for early smaller model, right? So we developed two reuse module. One is called the relationship reuse, and another is called the feature reuse. So basically, for the relationship reuse is because the vision transformers we will learn the attention maps, right? So there's the relations between different patches or different tokens. So these are informative. So these attention maps are quite informative, such that they can be reused for a later VIT. And then the feature reuse module is also so I think this part is relatively easy to know, because easy to understand, because we apparently can reuse some of the features we have learned so far in an earlier model, and to put them as the to facilitate the learning process in a later model. And so these are the detailed structure of these two reuse modules. One is for feature reuse and another for relationship reuse. I will go to the detail of these modules, and if you're interested, you can refer to our paper, which has already been put on arXiv. All right. So the performance is quite encouraging. Actually, the original VIT is not very competitive, and we directly compared with some of its recent variants, like the T2T VIT. It achieves basically 3.6 times speed up compared to some large T2T model, T2T VIT model, and all 1.6 times speed up compared to some medium-sized T2T VIT model. Okay, and actually, what I introduced is the dynamic architecture belongs to this category, and there's a lot of important categories called dynamic parameter. So like the dynamic VIT, the architecture is conditioned on the input, and there's a lot of possibilities. The network parameter is conditioned on the input, and I will have a brief summary of the key ideas behind the dynamic parameter network. So this is a illustration of a regular convolutional module. We have the input feature maps, and we have the convolutional filters. And there are the parameters are applied to the input feature to get the output feature, and the operator here is called a convolution. So this is the classical convolutional module. All right, and the first type of dynamic parameter network is we add the parameter adjustment module here, and the parameter adjustment module will adjust the original parameter a little bit, and the parameter adjustment is data dependent. That is, for different input, it will have a different adjustment, and then it will obtain a so-called dynamic parameter because the parameter adjustment module is conditional on the input, then such that the dynamic parameter, the final parameter is dynamic because it's conditioned on different input, and this dynamic parameter is applied to the input feature to get the output feature. Another dynamic parameter network is we have a dynamic ensemble of parameters. For example, we in a traditional convolution layer, we have one set of convolutional filters, and here we have multiple sets of convolutional filters, and these sets of filters is weight is summed up, and these coefficients are generated conditioned on the input feature. So basically, these coefficients are dynamic, right? So it's the values depends on the input. So basically, it's a dynamic ensemble of the original parameters, and this parameter is applied to the input. So this is the second idea to design the dynamic parameter to achieve dynamic parameter. And a more direct way is to directly predict the parameters from the input features. And this dynamic parameter predicted by the parameter prediction module is applied to the input feature. So this is the third type of achieve dynamic parameter in convolutional networks. And of course, another type of dynamic parameter network is deformable convolution. So if any of you have worked on computer vision, you may have heard about this type of convolution, which is has been very effective in object recognition. And this is also a typical type of dynamic network. And finally, perhaps the most widely used dynamic parameter network is those networks with attention mechanism, such as the transformer architecture. Why the attention is a type of dynamic parameter is because the attention is applied to reweight the feature maps, and actually reweight the feature maps is equivalent to reweight the weights, because the weight is applied to the input feature, and then the coefficients or the attention is applied to the output feature, and this is equivalent to first apply this attention to the weight, and then apply to the input feature X. So the attention mechanism is actually a special type of dynamic parameter network design. Okay. And in computer vision, one of the most successful attention mechanism is called squeeze and excitation, or SE net, and it has won the the ImageNet competition in the year 2018. So this is one of the most successful attention module in computer vision. And right now, the transformer is getting very popular, and is also based on the attention mechanism. All right. So far, we have talked about the sample-wise dynamic network. That is, the network architecture or parameters is conditioned on different inputs, and to make this dynamic computation finer, we can actually condition our computation on different pixels. So that's we call it spatial-wise dynamic network. And to see the motivation, we can first take a look at this image. And if we mask this image, we can recall what we have noticed from what we have recognized from the image. So we can easily remember that, recall that this is an image of a street view, right? This is a street view image, and there's a car in the middle, and there's a building behind. However, we may miss many of the details. For example, the color of the curtain of some window, right? And actually, if we go back to this image, we will see there's a motorcycle here, and there's a McDonald's on the right, and there are many details we may have missed in our first glance, right? So this shows that for the human visual system, we will allocate different amount of computation on different pixels. However, if we get back to convolutional networks, the computation spent on all the pixels are equivalent, right? So the convolution is we are scanned from the top left pixel to the bottom right pixel without any difference. So for example, if our task is we develop a visual recognition system for autonomous driving, then apparently we do not need to put much computation on the sky, right? We only needed to attend to those objects on the street. For example, the traffic lights, the pedestrians, the vehicles, right? And so that's why it's beneficial to develop a dynamic network, or to be more specific, a spatially dynamic network, which can allocate a different amount of computation on different pixels. And last year, we developed a network, a spatially adaptive network called sampling and interpolation. So the idea is actually very simple. It's just as the name suggests. We have so consider this is a module to replace the classical convolutional module. It has three key components. The first component is called a sampling module. It will generate a sparse mask M, and this mask is applied to sparse convolution module, which only performs convolution on given pixels that are indicated by the mask. Because the mask is sparse and the computation is also sparse. And once we obtain the sparse feature map, we will have an interpolation module to get a dense, to reconstruct a dense feature map. And since the most of the computation is spent on the convolutional module, and if we turn a standard convolution into the sparse convolution, we can save many of the computation And the interpolation model is very efficient, as the computation is neglectable compared to convolutional model. So with this model, it will be more efficient compared to a standard convolution. And the tricky thing here is the mask is binary and it's not differentiable. So we use the Gamble softmax trick to train this mask in an end-to-end fashion. All right. So if we replace the classic convolution by this sampling and the interpolation module, we can get a decent speed up on both object detection tasks and the semantic segmentation tasks. So this was a ECCV oral paper last year. All right, and then we make one step further. Actually, all human visual system process information progressively, and so actually the network we developed here, there's one downside, that is, as you may have noticed, the sparse convolution is not quite efficient on GPUs, right? Because so far the sparse convolution is not quite well supported on modern GPUs. So based on the observation that our human visual system process information progressively, we developed a so-called region level dynamic network. We still perform spatially adaptive computation, but the spatially adaptive computation is not conditioned on each pixel, but conditioned on different regions, such that this computation is more parallelizable. And we developed a two-stage framework, which is called the glance and the focus. In this framework, our first stage performs a fast global information retrieval. Its first downside is a high resolution image into a coarse level image, and we process with the convolutional network, and we get the prediction. And again, we can do the early access trick here. And if the prediction is quite confident, we can directly retrieve the prediction. Otherwise, we go through go to the second stage. And in the second stage, it will perform fine feature extraction of some local regions. For example, we will crop the head of the cat and to perform the feature extraction and to continue the recognition process. And in the local region, we can have multiple steps. We can crop multiple local regions. So as an overview, the first stage is called a glance, which extracts the global feature in a very fast manner. And then in the second stage, we will focus on different regions, and we will apply the early exit trick here to perform dynamic inference. So training this system is a little bit tricky, but I will give an intuition here. Right, so this is a full picture of our model, and so the most tricky thing here is where to look at, where to extract those local patches, and here we have the proposal network to do this job. And please note that this is for classification task, and we do not have the ground truth of the bounding boxes. This is not object detection where we have this ground truth bounding boxes. Here we only have the classification label. There's no bounding boxes. And in order to train this system, our first step is we first have a warm-up stage. That is, we remove the patch proportional network and only replace it by a random random cropping module. So the local patches are random, and then we fine-tune these convolutional networks, these backbones here, by minimize the cross entropy loss. And one note here is the backbone here, we can use any off-the-shelf convolutional networks. For example, the mobile nets, the efficient nets, anyone that your favorite. And we can use this pre-trained models and fine-tune them by minimize the cross entropy loss, where the local patches are just randomly cropped from the input. So this is the warm-up stage. And once we have finished the warm-up stage, we put the patch proportional network back and train this patch proportional network by a reinforcement learning process. So why we need reinforcement learning here is we model the local patch selection by formulated as an action in reinforcement learning, and the reward signal is how much error reduction we can get, and we maximize the discounted reward. That is, any questions from the audience?
我在听这个讲座。
Let's continue. So we formulate the local patch selection as a reinforcement learning problem, and the action is the horizontal location and the vertical location in this image, and the reward is just as mentioned, is how much error reduction we can get when we add a new patch, when we select a new patch to this system. Okay, and so the patch proportional network can be trained with reinforcement learning, and finally we just fine tune the whole system, fine tune the backbones, and the final classifies with the cross entropy loss. So that's all for the training process, and the performance are also quite encouraging. As I mentioned, the system, we can deploy any kind of backbone models here. So we, in our experiments, we have developed the MobileNet v3 as our backbone. So this is one of the most competitive, one of the SOTA models for mobile application, and we obtained quite significant improvements upon this model, and we also get decent improvements upon the RegNet, which was developed by Facebook last year, and we also get significant improvement upon the efficient net. And as I mentioned, this system is can achieve real speed up on real devices. So we tested the model on an iPhone device, and when we deploy the MobileNet v3 as our backbone, we can get speed up on this iPhone. And finally, this is the visualization. The last 4 images shown here is those easy ones that we can get the correct prediction from the glance stage. We do not need any local final feature extraction. We can directly obtain the correct prediction from the downsampled image. And the images on the right are relatively harder. That is, it leads to extract one local patch, and the image is shown on the on this side. The needed to extract 2 local patches or 3 local patches. Right. Finally, I will just briefly introduce some of our recent work on applying the dynamic neural networks for videos. That is, we can have a lot of dimension to perform dynamic computation. That is the temporalize. The motivation is that, you know, for video, we only a small portion of the frames have sufficient task relevant information, and many of the frames are actually redundant. For example, for action recognition. And so we developed a method called adaptive focus for efficient video recognition. And this is a framework. I want to go to the details of the architecture. So this is also based on the early idea, but it is a little bit different. Is that we use a policy network to select the important regions. So this is actually spatially adaptive, and also select the important frames. That is temporal adaptive. So with this network, we can achieve temporal adaptive and spatial dynamic, spatial adaptive simultaneously. So this also have achieved quite impressive performance on several video recognition data sets. And this paper has been accepted as the oral in SCCV this year. All right, so actually to achieve temporal-wise adaptive, the different ideas, some of them appears in the NLP community. And so I just listed the reference here. So if you are interested, you can take a look at those papers. So to summarize, there are many advantages of dynamic networks. First is computational efficiency. And then it has high representation power because the network can be conditioned on the input. So that's why this transformers, which is based on the dynamic parameter, which also basically is a dynamic parameter network. So it has higher representation power because its parameter can adapt to different inputs. And the dynamic network is more adaptive because it can adjust its computation online, condition on the environment. And it is also compatible with different tasks, and it can it is compatible with other with many different development in the in your field. For example, it can be compatible with different loss function design, can be compatible with the data augmentation techniques, and also is compatible with other like model other techniques to speed up the computational efficiency. For example, the pruning technique and the quantization technique, etc. And the dynamic network is quite general. It can be applied to many different tasks. For example, classification, detection, etc. And perhaps the dynamic network is more interpretable. For example, the spatially dynamic network, we can actually explain where the model is putting its focus on, which regions the model focused on. Right. And of course, there are many challenges in this field. For example, the relatively few theory paper on this topic, and there are many theoretical problems that are unsolved and unaddressed for dynamic neural networks. And still, the architecture design are relatively lag behind those statical deep learning. For example, many of the architectures are developed for static models, but they may not be suitable for dynamic models. And so far, some of the dynamic networks cannot be applied to detection or segmentation. It can be only be applied to classification. And also, there's a gap between the theoretical and the practical efficiency for some of the dynamic networks. And also the robustness and the interoperability may, I believe these are perhaps the opportunities here, because the robustness and the interoperability may, when we look into dynamic networks, we may have different view angles to improve the robustness or interpretability. Right. So our group has released a survey this year on this topic, and we think this is a relatively comprehensive survey on the topic of dynamic neural networks. And the paper has been put on arXiv. If you're interested, you can take a look at this survey, and we welcome any communications and on this topic, and welcome your feedback. Okay, so that's all. Thank you very much.
Thank you, Professor Huang. A very interesting talk. So any questions from the audience? I think we have one comment in the chat box.
Mm-hmm.
Yeah. So can you see that question?
Right. So the question is, any comments on the connection between dynamic networks and the model compression techniques such as pruning, e.g. results comparison of future for efficient. Okay, this is a very good question because in the field of efficient deep learning, I think pruning has gained more attention and has a longer history. It may date back to the 1990s. All right, actually these are two different angles to achieve the same goal, and actually they are complementary. So you can still apply pruning to a dynamic network to achieve higher speed up, right? So these are two orthogonal directions, and they can be complement to each other. And then so for the results, according to my experience, the dynamic network, I think, appears to be more competitive because it looks into the redundancy in the data set, right? So just as the two horses shown in my slides, there's some samples that are really easy that do not need a very deep model. So for pruning techniques, you still use the same model for all the samples, right? For example, you consider pruning a resonant 50. I think the most fertile results is perhaps on ImageNet. Okay, I think it's 2 to 3 times speed up. However, if as I'm shown, the first algorithm, the MSNet, it can achieve 5 to 10 times speed up compared to resonant. So the dynamic network explores the redundancy in the data set. It can achieve a significant speed up. Okay, so that's my opinion on this. So basically, they are both useful and they can complement each other. And second question is, how do you update a dynamic model with new incoming data? All right. So I guess you mentioning how to train a dynamic model with new incoming data, and in fact, so far most of the dynamic network are trained in a quite similar way as we train a dynamic model. As a static model. So basically, how you update a static model, then you can use the same way to update a dynamic model. And perhaps they exist some new ways to update a dynamic model, but so far I don't see any research have looked into this problem, right?
Any other questions from the audience? You can directly unmute yourself and ask a question. No questions? So actually, I have one question. So can you go back to the slide for your use the pixel level?
All right. I think it's. This one?
No, the pixel level. So use some new sampling the input feature and then perform the sparse convolution.
So I think it's this one, right?
Yeah, here. So I was wondering, so here actually you replace the ReLU, or this is the kind of addition to the ReLU?
This is only replaces the convolutional module, so it does not touch the ReLU. Does not touch the ReLU layer.
Okay, so in that case, because for example, for our input feature, it already kind of like to the output of the ReLU, right? And in that case, so the input feature is already be kind of the sparse.
Right. So I guess you were thinking about how to leverage that kind of sparsity, right?
Yeah, and also so because we can view that the ReLU is kind of already kind of the deterministic sampling. So if we continue to perform the another type rounds of sampling, whether it can be, and we will lose kind of too much information here.
Actually, for image data, the spatial redundancy is quite, there's a significant amount of redundancy. So the ReLU layer may not be sufficient to filter out this computation. And for example, like in this image, we may still need to extract the features of the human body, right? But perhaps all these features are not muted by the ReLU, so it may still output positive values for the region corresponds to the human body. And in this algorithm, it may just compute some of the key points, and it can interpolate the features between these points, right? So it's more powerful than the ReLU.
Okay, I understand. So it looks like it's kind of when you do this, the sparse sampling is type the regularization, right? And then to perform the reconstruction, then can gain the better presentation of the original image.
That's true.
Interpret it using this way. And another additional question, so when we perform the reconstruction, so how about the computational cost?
So the interpolation is very efficient. So basically, the computation is neglectable because in convolution you have the convolution is basically you have a lot of mile-add operations, right? And it's all across the channels. And interpolation, you just take each independent feature map, and you can perform the bilinear interpolation or other interpolation algorithm, which is very simple. It's very efficient. Yeah.
Okay. Thank you. And
Yeah.
any other questions from the audience? If not, other questions. Actually, I have another additional question. Yeah. So just before your talk, so we chat about the difficulty of the dynamic training. So in your experience, so what's your comments or the vision of that? So why the dynamic training is kind of relatively difficult than the dynamic inference?
Right. So far we have many, as I mentioned, we have many unsuccessful tries. So I think like during the inference stage, we can save the computation on those easy samples, right? But during training, if we remove some of the easy ones, it seems that the network will lose the ability to I don't know, maybe to models to extract those specific features. So we have done many experiments. For example, we in the MSD net structure, just shown here. What we tried earlier is that we first trained the network for a while, so it has some basic ability to differentiate those easy samples and the hard samples, and then we only train the classifier one, the shallow classifier with those relatively easy samples, and train a deeper classifier with those harder samples. That is, we do not compute the loss for easy samples in deep classifiers, and we do not compute the loss for difficult samples in the early classifier. And all this experience leads to worse performance, and all kind of immature conclusion is the harder ones is obviously important because those may be those samples lying near the classification boundary. They're very important to learn the correct decision function. And those easy samples are kind of like regularizing the loss function, the function learning process. And right, so it's kind of I don't know. So actually, our intuition is that it should help. For example, the first classifier never needed to infer the harder samples here, right? But when we remove the harder samples in the training process for this classifier, then the performance will decrease. Yeah. Yeah. So far, we still do not have very concrete conclusions here, and we believe is an important topic, especially for training those large classifiers. Like nowadays, we train transformers. We needed to train hundreds of epochs, and the models are very big. And so this is a very, important problem, but so far we do not have quite much ideas. Yeah.
Thank you for sharing your understanding and observation. So there's another question.
That's, right in the tab. The question is, to evaluate the dynamic inference, is there any way to guarantee the theoretical compute complexity reduction using big O? Typically, latency and flops reduction are the common ways to evaluate this. Right, I think currently we do not have much theoretical guarantee for this. We're actually working on this. Hopefully we'll have some theoretical results, but so far we basically report this, the results are quite empirical. Yeah.
Thank you. Any other questions from the audience? Okay, so if no more additional questions, so let's thank.
Actually, I have a question about the dynamic neural network. So the dynamic neural network depends on the inputs. So in reality, for example, how can we control whether we have different inputs, then we trigger different part of the neural networks in hardware? Does it affect the latency of the inference? Because you need to, for example, you have an input and you need change the neural network somehow depend on this input. But this dependence somehow, if it is implemented with hardware, then this hardware will affect the inference time, which means the latency to get the output, right?
Mm-hmm. Right. So yeah. So the latency is different for different input. So if you look at the maximum latency, then perhaps it can give you no gain, because there's some hard examples that the latency cannot be reduced. But if you look at the energy consumption, you may still have it may still have some advantage.
Okay, but you did not consider about the hardware to implement such control logic, right?
Right. I'm not quite familiar with the hardware. I think you know, you can implement this idea on hardware to save energy and to cut down the latency for some of the samples. But the maximum latency perhaps you cannot be reduced.
Okay, thank you.
Thank you.
So maybe I can help answer this question from the perspective of hardware. I also work on the customer hardware DNA accelerator. So I think it depends on what is the dynamic strategy you use. For example, if you just use like the skipping layer, I think from the perspective of hardware, so the additional control logic overhead is kind of minor.
Yeah, but if you don't use the early stop strategy, you just change the, for example, some part of the neural network is triggered when a special input enters the neural networks. So in this way, somehow the control logic is complicated, right?
Yes, for the control mechanism, yes, it will be complicated. But when we like to compare with the entire neural work, hardware complexity, I think it's still kind of very, very minor, because if we consider about like the energy consumption, the dominant part will come from like the data, the memory access, right? So if you consider about the computational cost, so the main contribution will come from like the systolic array. So for the control part, so I don't really implement dynamic network, but based on my knowledge and my expectation, I think the control part, the additional cost, when we change the control part, it should still be kind of the relatively small.
Okay, did you evaluate it already?
No, I have not done that before, yeah.
Okay, okay, thank you.
You're welcome. So any other questions from the audience? Okay, so if no more other questions, so let's thank Professor Gao Huang again for this very informative and very excellent talk, and also thank all the audience to attend our this week's seminar. So see you next week. Thank you. Thank you, Professor Huang.
Thank you. I also learned from your answer. I learned a lot from your answer. Okay, good. Thank you. Thank you very much.
Thank you, everyone. Thank you.